Hi class, we are on 19.10. We're on the last section. We're going to be looking at free energy and equilibrium. So in the previous section, I had discussed that at equilibrium, the delta G, the free energy is equal to 0. And that's because the free energy ceases to change at that point. Remember looking at an equilibrium constant, which is K. If K is less than 1, then the delta G is, the free energy is positive, and the reaction is spontaneous in the reverse direction under standard conditions. Again, something that I briefly covered, more looking at Q on on those reactions. Excuse me. I'm sorry. Very rude. So if K is less than 1, the free energy is positive, the reaction is spontaneous, and the key thing being in the reverse direction under standard conditions. When K is greater than 1, the free energy is negative, and the reaction is spontaneous in the forward direction under standard conditions. And again, if K equals 1, the equilibrium constant equals 1, the free energy is 0, and the reaction is at equilibrium under standard conditions. This is very similar to what I showed on the last section. Remember, we have free energy. We have higher free energy here, which is B, and it slowly it decreases until it gets to equilibrium. And where it gets to equilibrium is more towards A than it is towards B. So it's more towards, in this case, the reverse reaction, and when it's at equilibrium. So this would be spontaneous in the reverse reaction going this way. If we look at this one, you see we have a lot of free energy, and it decreases until it gets to equilibrium here. And by this point, it's mostly in products, which is pure B. So this is a spontaneous in the forward reaction. And here it's at equilibrium, which is the free energy is equal to 0. It's in the middle at this point. K equals 1. So when a reaction is at equilibrium, the free energy is equal to 0 and Q equals K. We can substitute these into this problem, this formula. So if we have this here, we can make it equal to 0. And then we have Q, and we can make it to K, which is our equilibrium constant. Then we can make these equal to each other, and this is where we get this bottom problem, which I think is 19.13 in your book. Now again, just to go over these, when the free energy is less than 0, then that means that the equilibrium constant is greater than 1. When the free energy is equal to 0, the equilibrium constant is equal to 1, which means it's at equilibrium. And when the free energy is greater than 0, then that means that K is less than 1, and that tends to be spontaneous in the reverse reaction direction. And this is simply stating the same things, just repeating it over to help you understand that what these conditions are, because they can be a little confusing at the beginning. This is also a graph, just a little different than the other one, but the same things being shown. When delta G is less than 0, you can see that the free energy ends mostly towards the products over the reactants, so this is spontaneous in the forward direction. Delta G is at equilibrium, and when the free energy here it decreases more towards the reactants, so the equilibrium is this is a spontaneous reaction towards the reverse reaction. Sorry, spontaneous. Okay, so what if we want to calculate the equilibrium K from free energy? Well, we can take this reaction, let's go back, and solve for the equilibrium constant. So the natural log of the equilibrium constant. So we can isolate this, move this over, and we can solve for the equilibrium constant if we didn't have it. And that's what you see here. And then what we do is we take the inverse log, and that will set this up as E, and we can solve for this here. That would be a superscript now. So that's what we're going to do. Calculate the equilibrium constant for the Haber process at 298 Kelvin. So from the delta G in the previous sections, I've showed you how to get that from data, from the free energy or formation data. And I've given the answer here to make this easier at this moment. And we're going to solve for the equilibrium constant. So we're going to take this equation, plug everything in. Now remember, for this, we're solving for E. So what you see here is for the exponent. This is for it, what would be in the superscript or exponent. So we're going to solve for that. There's a negative sign, but this is negative, so you're going to have the two negatives. We have our gas constant, our Kelvin. We are converting from kilojoules to joules, and that's going to give us a value of 13.24. But we're not done, because all we solve for here is the exponent. So we need to plug that in. So from here, we can use the calculator, and it's going to give us our equilibrium, which is 5.6 times 10 to the 5. So this is a very large equilibrium constant, which means it's going to be mostly in products, because remember, it's more than one. So it's going to be more towards products, spontaneous, and more towards the products. So forward direction. So a review, free energy changes under non-standard state conditions are calculated according to 18.10. And I apologize, this is from another slide in another book. I should have corrected that. Where Q is the reaction quotient, but you see it right here. And this is what we used in the previous section. Now, when we wanted to determine standard free energy changes that are related to the equilibrium constant, this is where we'll use this. I thought I changed these. I apologize. But we use this here. So now we have different ways of solving for what it is.